Okay, good morning friends. Today we'll just discuss about the gate logic. So gate logic are the three basic gates are what your NOT gate, that is inverter, AND gate and OR gate. Okay, so since we people have been designing by using the complementary metal that is CMOS, so we'll just considering the NAND and NOR. So first we'll convert to the inverter, next NAND and NOR. We'll just go through the basic structure of your schematic as well as your stick diagram. Okay, now we'll just discuss the inverter. In that we'll be just going through first the NMOS, later the BiCMOS as well as your CMOS. Okay, NMOS structure. Okay, first the inverter. Inverter is having only what? One input, so we require one PFET as well as one NFET. Okay, first to draw this, first we require one demarcation line. So this line is the one which differentiate the P structure as well as your N structure. Okay, and always the demarcation line. So the PFET should be placed always above the demarcation line, and the NFET should be placed below the demarcation line. Okay, always the PFET should be placed above and the NFET should be placed below the demarcation line. Okay, next. Now we'll just represent the terminals of your FET of a PFET: gate, source and drain. Okay, since it is a logical high device, the PFET always the source should be placed above, and since it is a logical low device, okay, so NFET should be placed, that the source should be placed below. Okay, so these are the treatment. Next, the connections, okay, of a NMOS. Okay, since it is a NMOS, we will just considering the giving the only inputs at the NFET, not the PFET. Okay, next. So the connection source, the NFET should be always grounded, as we know that, and always the PFET should be placed with the connected with the VDD. Okay, and the two drain region should be shortened, and we should take the output. So this one is our V out. Okay, next, see, source is being connected, the PFET source is connected with the VDD, and the NFET source is connected with the ground, and the two drain regions are being shortened, and we have taken the output. Remaining is the input connections. Okay, and since we are just giving the input at the NFET, see, in NMOS, the gate region of a PFET is shortened with the drain region of the PFET. Okay, so this one is the important point in your NMOS. The gate input is being shortened with the D. Okay, so what are the always whenever the means V in, if I just give the input as 0, my NFET will be in a off state. Okay, so there will be no connection. Okay, since the gate is being shortened to a drain, the VDD is being connected, and the PFET will be on, and we will be just getting the output as V out is equal to 1. When the Vin is equal to 0, we will be getting the V out as 1. When Vin is equal to 1, when Vin is equal to 1, the NFET is being on. Okay, and the capacitor starts discharging, and what V out will be reduced to the ground, so we will be getting it the V out as 0. When the Vin is equal to 1, V out is equal to 0. So this one is the structure of your NMOS. Okay, in the same fashion in CMOS, what will happen? The same thing. First the demarcation line. Okay, next one PFET, one NFET, and already people know the connection about this one. Okay, since it is just roughly drawn. Okay, next, since same thing, so always the PFET should be placed above and NFET should be placed below, and the PFET is being connected with the source of this PFET is connected with the VDD. If I just represent the terminals, gate, source and drain, gate, drain and source. Okay, next, the source region of a PFET should be placed above the VDD, and the source region of a NFET should be grounded, and the two inputs should be connected, and it is be shortened, and we will be giving it as the V in, and the NFET the two drain region should be shortened, and we taking the V out. Okay, so this one is the connection for the CMOS. So when V in is equal to 0, what will happen? When V in is equal to 0, my PFET will be in a on state, since it is a logical high input value. Sorry, it's a logical low input value PFET. Okay, when the Vin is equal to 0, my PFET will be on. So PFET is on means, so this FET will be in a connected, and this one will be an off state, means there will be no connections between the two. So Vin is equal to 0 means this is PFT will be on and VDD will be shortened with the V out. So the capacitor will be charged and we will be getting the output as 1. So when the Vin is equal to 1, what will happen? My PFT will be in a off state and then FT will be in a on state. When then it is in a on state, what will happen? The source regions are being shortened here, okay, and the capacitor, whatever it is charged, will be discharged to ground. So V out is equal to 0. When Vin is equal to 0, I will be getting the V out as 1. Okay, next we will just go through your by CMOS structure of a inverter. Okay, so these are the components required: one PFT, one NFT, the same thing what we will be having. Next, along with that, we will be having two NPN transistor. Okay, so this one is the structure, and just go through the connections. Okay, and these are the terminals: gate, source, and drain. So this one is gate, source, and drain. Okay, now as you already know that the two inputs should be just shortened and just giving as the input. Okay, in a by CMOS. Next, the source regions of a PFT should always connected with the VDD, and in this structure the NFT source is also shortened with the VDD. So this one is important. Okay, next the gate region is over and the source regions have been over. Next, the drain region. So this drain region is acting as a input to the base of a next transistor. Okay, next the drain region is acting of NFT is acting as a input to the base region of a next transistor. Okay, next the collector part is connected with the VDD and the emitter part is being connected with the VSS, and the output is being shortened and we are just taking the output. Okay, so this one is the structure of your by CMOS, how it looks like after connection. The two gate regions are being shortened and given the input. The two source regions are being connected to the VDD. The drain region is acting as a input to the transistor, that is of a NPN transistor, and the two transistors are shortened. We are just taking the output, that is your Vin equal to V out. Okay, next, so these are the structures what you just looked up previously, that is NMOS, BiCMOS, and CMOS. Okay, so in NMOS what is happening means we are only concentrating on the NMOS, that is we are just giving the input towards only the NMOS only. So if any number of inputs, so since it's the input inverter, we are having just only one input. If we are taking the N and out, so it will be having two inputs. At that time only there will be only one PFT, and that PFT is always shorted to a drain region, that is of your V out. So V in this. So this one is your by CMOS. So one PFT, one NFT. Next, two NPN transistor. The gate regions are being shortened, so we are giving it as a input V in. The two source regions are being shortened with the VDD. Next, the drain region is acting as the input of a transistors, and the two transistors are shortened. We are taking the V out. Okay, next CMOS. So complementary metal oxide semiconductor. So these are the two structures what they are just represented. Depending upon the flow of direction, flow of electrons, whether it's a PFT or NFT will be just different. If the flow of electrons, that is measured outside, then it is be PFT, and if it is inside, then it is the NFT. The simple thing what will be represented by the bubble for PFT, and there will be no bubble for your NFT. Okay, so just structure. So V in, so two gate regions are being shortened. The two source regions are connected with the VDD and VSS, and the two drain regions are shorted, and we are taking the output. When V is equal to 0, what will happen? When V is equal to 0, PFT will be in on state and NFT will be in off state. Off state means there will be no connection. So on state means there will be a connection between VDD as a V out. So there will be a capacitor, and that capacitor will be charged, and we will be getting the V out as 1, because 1 means the VDD. Okay, next, when V is equal to 1, what will happen? The PFT will be in off state, and V is equal to 1, the NFT will be in a on state. So V out is being connected with the V out, that is the capacitor, whatever it is charged, is discharges to the 0. So we will getting, when V is equal to 1, we will getting it as a 0. Okay, when V is equal to 0, we will be getting the output as 1. When V is equal to 1, we will be getting it as the, okay, C. Now these are the logical symbols of the representation of a NMOS, BiCMOS, or CMOS. Logical symbol is almost same, only the internal structure varies. For NMOS you will be having what? The PFT will be shortened. In BiCMOS you will be having two extra NPN transistors, and in CMOS the same thing. So only two FETs, one PFT and one NFT. FET. Now we'll just go through the next, the stick diagram of how it will be represented in NMOS, BiCMOS and CMOS. Okay. Now we'll just discuss about your stick diagram. Okay, so this stick diagram as well as your layers already people have read in your module 2 about the design tools. Okay, stick diagram or the layers will be having a two type, that is monochrome or the color chrome. Monochrome means you will be just representing by the different structures represented, and in a monochrome means we people the same thing will be just represented by the color chrome. Okay, in your stick diagram, okay, see here in the representation with the field one is only representing your metal. Okay, and it will be in a color chrome, it will be of a blue color, and it is always used for your connection parts, or only for the connection parts which require the metal, as well as to represent the output. Okay, next the structure with the dotted points is known as your polysilicon, and it is of a red color, and the polysilicon always represents your gate region where the input will be given. Okay, and the structure without anything is known as your representing your diffusion part, that is your N plus or the P plus. Normally if it is of a green color, okay, and it represents your drain and source. Okay, next, when is the transistor is formed? Whenever the polysilicon crosses over the N plus or the P plus diffusion, then the PFET or a NFET will be formed. Okay, only this part. So wherever the polysilicon is crossing the diffusion, this part is acting as your transistor. Remaining all steps are been just for the connection. Only this part where the polysilicon crosses over the N plus or P plus, that part is only acting as your transistor, that is it might be PFET or your NFET. Remaining things just for the connection purpose. Okay, and this represents your BiCMOS structure. Okay, the dashed lines, these things, as well as your gate region will be with the dotted line. This represent your source and drain. Okay, so this one is the important structure of your BiCMOS. Wherever when you will be representing the BiCMOS, so this structure is being required. Next, the later the connections, how the connections will be made for a PFET or the along with the NFET. So this one is the structure. So source, gate and drain region. Okay, this is the schema stick diagram structure. Okay, so we have represented the by using VDD and VA ground by using the metals, and the gate regions are being represented by your polysilicon with the dotted lines. Okay, and the structure with these two NFET as well as your PFET, that is the N diffusion as well as the P diffusion. And another thing, the VO should also be represented with the dark lines, so that it is for your VOut. Okay, see the structure here. Next, so this one is same as your, means the stick diagram is exact replication of your schematic diagram. Okay, next, see here, for this, since it is only a NMOS, so only the NMOS structure, at the NMOS structure only we should give the input, so we are just given the input. Then the PFET, since it is a NMOS, the PFET should be grounded to the drain region, so the PFET, the gate region, is being short onto your drain regions. Okay, and the source and the drains are being connected with the VDD as well as your ground, and then between two PFET as well as NFET, the output should be just considered. Okay, so this one, it is exact replication of your stick diagram. Okay, see here. So this one, the schematic representation is same as your stick diagram. Okay, see here, the VIN is given towards the gate region, and the gate of a PFET is being short onto the drain regions. VDD and VSS have been connected. VDD and as well as VSS have been, that is the ground is being connected, and the VOUT has been taken as the output. Okay, see the between two, the VOUT has been taken. So it is exact replication. The schematic is the exact replication of your stick diagram, or the stick diagram is the exact replication of a schematic diagram. Okay, and so here with the things what you are representing as with the dotted lines, it is known as your polysilicon, that is acting as your gate region, with the dark lines are known as your VDD as well as the ground. Okay, next, so without anything, it is known as your diffusion part, that is your FET. Okay, and this part with the dotted line is known as your N well region or the implant region. Okay, now we will just go through the by stick diagram of your by CMOS structure. Okay, so before going that, we'll just go through the by CMOS structure, that is represented as a rectangular box. The first part is acting as a source, the dotted line is acting as a gate, and the next part is acting as your drain region. So this one is the symbolic structure. Okay, the same thing it has been represented here. Okay, see here, it is acting as the source, gate and drain for a PFT, source, gate and drain for your NFET. And since it is a BiCMOS, so along with that we require two NPN transistors. Okay, and since it is a BiCMOS structures, okay, the two gate regions should be shortened, and the two gate regions are being shortened here, and the input is being given. Okay, next the source region of a PFET should be connected to the VDD along with the NFET to the VDD. So these two are being shortened and given to the VDD. Okay, next the drain region of NFET as well as PFET as well as the NFET should be connected to the base of the transistors. Okay, see here, the PFET drain is connected to the base of the transistor, and NFET is connected to the base of the transistors. Okay, now the two transistors are being shortened and the Vout should be taken here, as well as the VD1 should be connected to the VDD and the other should be connected with the VSS. Okay, see, now we will just go through the the schematic representation of your BiCMOS, how it will be just compared. As you already told, the two gate regions should be shortened here, the two gate regions are being shortened and given the input. Next, the source regions are being connected to the VDD. See here, the two source regions of a PFT as well as NFT is also connected to the VDD, and the drain region is being connected to your the base of the transistor. The two regions are connected to the base of the transistors. In between these two, the output should be taken out, and the VDD as well as the VSS are being just connected. Okay, for the simple BiCMOS. So this one is the structure, very much important. Just see the schematic of a CMOS inverter and the stick diagram for CMOS inverter. Okay, see here, so there is no resemblance between this schematic diagram as this stick diagram. Why? Because here the gate region is being placed horizontally and here the gate region is placed vertically. Okay, though the operation is being same, but there is no resemblance between this schematic as well as this stick diagram. So here the difference is between horizontal as well as the vertical schematic. Okay, now so if you want to draw the horizontal schematic depending upon the gate region, if the gate region is placed horizontal, then it is known as the horizontal schematic diagram. Okay, the same diagram of a PFT, if I just turn up, then it will be representing the gate region is be placed above. So this one is representing the vertical. So this one is known as your vertical. Okay, so this one, whatever the stick diagram has been drawn, we'll just go through now the vertical schematic of a inverter and then compare with your stick diagram. Go through the vertical structure of your CMOS inverter. Okay, as I've already know that. So first the demarcation line should be drawn. Okay, so above the demarcation line the PFET should be placed. Since it is a vertical, the structure changes. Okay, it should be, the gate region should be placed vertically. Okay, so this represents my gate, source and drain region. In the same fashion, below the demarcation line the NFET should be placed. So this represents your gate, source and drain. Okay, so PFET is placed, the NFET is placed. Okay, now the connection purpose. Okay, as you all know, response inverter is having only one input, the two gate regions should be shortened and the Vin should be given. Okay, at the source region what, the VDD should be connected, and the source region of NFET the VSS or the ground. Okay, now the output should be considered for the two drain region should be shortened and the Vout should be taken. Okay, so this one is the schematic represent or the vertical structure of a CMOS inverter, and this represents here. So this represents your the CMOS stick diagram, and this one is your CMOS schematic vertical. So these are the two vertical structures. So Vin, the two gate regions are being shortened, the two gate regions and Vin is again given. For the source region VDD is connected and the source region of NFT VS is being connected. So see here, the two drain regions are being shortened and taken as the output. The two drain regions are being shortened and taken as the output. So this one is your CMOS inverter. Okay, so these are the three structure how it will be looking. The CMOS by CMOS as well as the NMOS stick and symbolic diagram. Okay, see here, stick diagram. The gate is of NMOS means the gate region should be of a PFET should be shortened. Only that the NFET with the union will be given. So this one is the structure of your by CMOS, and this one is the by CMOS structure. That is, this one is your vertical stick diagram. Just go through an alternate of 8:1 NMOS inverter. Okay, so this one is a pull up transistor and this one is your pull down transistor. Just will calculate for your ZP, that is the impedance of a pull up transistor is given by the formula L by W, length of a pull up transistor divided by width of a pull up transistor, that is by 8/2. So we will be just getting of a 4 lambda. Okay, next the resistance of a pull up transistor is given by ZP into sheet resistance, that is R, that is your 4 into 10 kilo ohm. Okay, so sheet resistance, standard resistance, sheet resistance is given it as 10 kilo ohm. Okay, similarly for the pull down transistor, what ZP is given by the LPD divided by your WPD, that is your length divided by your width. So they will be getting it as a point. So the resistance of a pull down transistor is given it as a 5 kilo ohm. Okay, next the power dissipation formula is given as V square divided by RPU plus RPD. Okay, so this one represents your plus sign. So the voltage will normally consider it as a standard one, that is your 5 volt. So we'll be getting it as 5 volt, 5 square divided by, so the ZPD is your 40k plus 5k. So we'll be getting it of a 0.56 milliwatt. Okay, and the input capacitance is given by the 2 gate capacitance. Okay, for this figure. Okay, so this one is your length and this one is your width. Okay, the next, so the same problem for the next thing. So here also see here, so it is the length is of your 16 lambda and the width is of a 2 lambda. For the NFET it is of a the pull down transistor it is of a 2 lambda. Okay, so the width is been common for your pull up transistor as well as the pull down transistor is your 2 lambda. Only the length is been changed from 16 lambda to a 2 lambda. Okay, if you just put it in the same formula and if you just calculate, you will be getting ZPU, that LPU, that is 16/8, and the resistance of pull up transistor is your 80 kilo ohm Z pull down. So the input capacitance what you will be getting after the power dissipation formula is of a 0.6 milliwatt. So input capacitance is of a 1 gate capacitance, that is a 1 square gate capacitance.